We will keep talking about trends in the periodic table in terms of looking at the elements from a general perspective. We have talked about atomic size and ionization energy, and I hope that now you may start connecting the dots, because notice that the the smaller atoms are typically they are smaller because they attract the the electrons more strongly, and therefore they have a larger ionization energy. So the whole trend in here is that the closer the electrons are to the nucleus, or the higher the positive charge of the nucleus, the smaller the element will be, and the higher the ionization energy will be. We have not talked about the electron affinity, and it's because it has so many exceptions that it's not even worth it to try to make sense out of a property that it's barely periodic. Just so you know, the electron affinity for an element is the energy that it takes or that it releases once you add an electron. As we said, the electron affinity, it does not follow a trend, so we will not talk about it. But the atomic size and ionization energy, they are complementary. They're talking about the same. And that same property is all described in one property called electronegativity that tries to refer to that. A smaller atom, or an atom that has a higher ionization energy, it means that it's an atom that is very much attached to its electrons, and that will affect the capacity to share, to give away those electrons, or to capture other electrons. So typically in this area of the periodic table, the upper right part, you will see small atoms with a higher ionization energy. That is, atoms that are not willing to share those electrons. We will say that those atoms have a higher electronegativity. And a higher electronegativity, there's some exceptions, but typically implies a higher ionization energy and a smaller size, and with the size being an exception sometimes. Okay, it's important to understand, however, why some elements have a higher electronegativity than others, and always boil it down to the attraction between electrons and the protons in the nucleus. Because sometimes I may not like the term electronegativity, because for sodium there's only one number. However, sodium 0, the neutrals sodium and sodium plus, well, they behave very differently. And so electronegativity may not have the prediction power that we'll have when we think of sodium and sodium plus with its elements, with its electrons, excuse me, and its protons. The reason why sodium plus is so stable is because it has a full shell. The reason why sodium reacts so violently with water is because it has only one single electron, therefore that tries to get rid of. So hopefully you may start knowing the elements based on where they are and how many electrons they have and how close to the nucleus those electrons are. There's along with electronegativity, there's another property that is very much related, which is called the metallic behavior. If you think about metals, what metals are typically shiny solids, and they have relatively high melting points, and importantly, they tend to lose the electrons. So metallic behavior is a property that, if you think about it, is the opposite of electronegativity. We said that in here, in this upper right part of the periodic table, will be the elements with high electronegativity and willing to give away the electrons. The metallic behavior will be the opposite. In here, in this corner, you'll have a low metallic behavior, and on this end you will have a very low electronegativity, or what's the same, a very high metallic behavior. And that's knowing a lot of chemistry. If you can just predict some behavior of a specific element based on the position on the periodic table or the amount of electrons, that will tell us a lot. Okay. There is, however, a trend. This is a trend. You cannot say, unless it's right here like fluorine, you can say that fluorine is a completely non-metallic, or cesium here is a complete metallic. But there is a gray area here, and the area that is most gray, if you will, is the so-called the metalloids. The metalloids is the elements that are right here at the border, in which if you go from a higher, sorry, from the 2p, the 3p, and the 4p, and so on. So you go down the p block, you will see that nitrogen is a non-metal, and then phosphorus is still a non-metal but less non-metal, and arsenic and antimony. This is start as you go down the p block, you will see a complete change of behavior. And the same goes for the second period. In this case, it's the third period. You start with metals and you end up with a complete non-metal such as the chlorine. So the area where this changes is called the metalloids, or false metals. And while again this is a very coarse description, because it's, as we said, it's just a gray area. You cannot say that an element is 100% metal or is 100% non-metal. This will help you understand when you can expect some elements to behave like metals. They conduct electricity, they have higher boiling points and higher melting points, etc. Okay, so take-home message: expect these elements to sometimes behave like non-metals or sometimes behave like metals.